Hi everyone, this is a new release of free scientific information for you, our dear Blogmaster. Today we are going to talk about the speed of sound, an important application of this in the aeronautical world. Well, the speed of sound is the distance traveled per unit of time of a sound wave propagating through a medium. We are just going to focus on air. However, the speed of sound varies from substance to substance. Sound travels faster in liquids and non-porous solid than it does in air. If we compare the speed of sound in air at 20 Celsius degrees, it's 4.3 times faster in water and nearly 50 times faster in iron. And why is this? This is because speed of sound depends on density and pressure of the medium. Like pressure and density depends on temperature, speed of sound finally depends on temperature. So this means that speed of sound increases if temperature increases and decreases if temperature decreases. The speed of sound at certain conditions is called the local speed of sound. And how we obtain the local speed of sound? Well, the local speed of sound is obtained by the following formula. The speed of sound is equal to the speed of sound at 0 degrees, which is 331.3 meters per second, plus 0.606 times the local temperature. Well, with this formula, we can obtain the speed of sound at different conditions. For example, the speed of sound at standard sea level condition corresponding to 50 Celsius degrees of temperature and 1 atmosphere of pressure, the speed of sound is 340.3 meters per second, 1225 kilometers per hour, and 661.5 knots. After all of this, why do we need the speed of sound? This is because the speed of an object divided by the speed of sound is represented by the Mach number. Thus, Mach number is a dimensionless quantity representing the ratio of velocity of an object and the speed of sound in the medium that said object moves. That's why we use the speed of sound. The speed represented by Mach 1 is not a constant. It is dependent on temperature. As stated before, the speed of sound increases as the ambient temperature increases. So, the actual speed of an object traveling to constant Mach 1 will depend on temperature of the fluid through which the object is passing. For example, an aircraft traveling at 10,000 feet and 5 degrees of temperature will reach the speed of sound, this means traveling at Mach 1, at a higher speed than other aircraft traveling at 36,000 feet and minus 50 degrees, which will reach the speed of sound at a lower speed. And would you say, why do we need the Mach number? This relationship is important for airplanes. Depending on the Mach number, the flight will be differently classified. As you can see in the table, subsonic flight has a Mach number lower than 0.8, transonic flight between 0.8 and 1.2, supersonic between 1.2 and 5, hypersonic between 5 and 10, and high hypersonic between 10 and 15. We are going to focus on supersonic flights. What happens when an airplane exceeds the speed of sound?
When an aircraft exceeds Mach 1, a large pressure difference is created just in front of the aircraft. This abrupt pressure difference, called a shock wave, spreads backward and outward from the aircraft in a cone shape, a so-called Mach cone. It is this shock wave that causes the sonic boom heard as a fast-moving aircraft travels overhead. A person inside the aircraft will not hear this. It is characterized by an abrupt, nearly discontinuous change in pressure, temperature, and density of the medium. Because of this amplification effect, a shockwave can be very intense, more like an explosion when heard at a distance.
That's all the information that we have for you today. Hope you enjoy and learn how to fly at the speed of sound. Maybe in the next video we show you how to build at home an airplane in order to reach that speed of sound. Who knows? Thank you for watching Vlogamaster. See you next video. Bye bye.